Welcome to part 2 of our discussion of key transforming operators in RxJava's Observable class. These operators can be used to transform the values and/or the types that are emitted by an observable. And we'll talk here about the flatMap and flatMap observable operators. We'll also describe the RxJava concurrency idiom and show how that can be used to increase parallel processing in an RxJava program. The flatMap operator can be used to transform the elements that are emitted by an observable asynchronously. The items that are emitted are based on applying a function, which is passed as a parameter, to each item that's emitted by this observable. That function, if you take a careful look at it, returns something called an observable source. And all the observable sources are merged together, and the results of this merger are emitted by the return observable that comes back from flatMap. As a consequence of the way things are merged together, the results can interleave. So if you have multiple observable sources, you may have the results interleaved in some way. Moreover, the number of output elements may differ from the number of input elements. They could be the same, they might be equal. There may be more output elements than there were input elements, or there could also be less output elements than there were input elements. It all depends on what your function does. Moreover, flatMap can transform the values and/or the types of the elements that it processes. So it's very powerful. The flatMap operator is often used to trigger concurrent processing, and we'll talk more about this shortly, a little bit later in the lesson. Here's an example which we'll take a look at when we get to the case study at the end of this lesson that shows how flatMap can be used to return an observable to a multiplied big fraction using the RxJava flatMap concurrency idiom. And you'll see this is a pretty cool technique. Project Reactor has a flux class whose flatMap operator works in essentially the same way as RxJava's flatMap works. These work similar to, but not really quite identical to, the flatMap method that's defined in Java streams in its stream interface. Here's an example of using a stream flatMap to be able to take two lists and flatMap them or flatten them. So we end up, rather than having a stream of lists of strings, we end up with just a stream of strings. One of the interesting things to remember about flatMap is it doesn't ensure the order of the items in the resulting stream because they're essentially merged together. If ordering is important, if you want everything from one source to appear before all the elements of another source, then you should probably consider using concatmap instead of flatMap. There's some benefits to flatMap, though, because you can get faster performance because you don't have to worry about concatenating things. So it's a little bit more lean and mean, if you will. Let's now turn our attention to the flatMapCompletable operator. This will do a flatMap of an observable into a completable. As you can see here, what it does is it maps each element of the current observable into completable sources. And then it subscribes to them and waits for the completion of all the upstream and all the completable sources. So it's basically waiting for everything to finish. It returns a new completable instance indicating that it's finished. The completable return values wait for the upstream's observable terminal event, basically waiting for onComplete to finish. We typically use the flatMapCompletable operator in conjunction with the async task barrier because it's a way to indicate that an operation is done running asynchronously, or more specifically, a chain of operations on an observable stream have finished processing. Therefore, the completable won't be triggered until all the asynchronous processing is done. And you'll get a chance to see this when we get into the examples we'll take a look at later. But we'll take a look at some of the examples at the end of this lesson and some other ones too that will show how all these things can be used together to give you very powerful techniques for waiting for operations to finish running concurrently. Interestingly enough, Project Reactor has no comparable operator to flatMapCompletable. However, it does have a then operator in its flux class, and it has a then operator in its mono class that provide similar capabilities when they're used in conjunction with Project Reactor Flux's flatMap. So be aware of that. And if you take a look at the Reactor code I have as part of this course, you'll also get a chance to see how those things work too. The completable future all of method can be combined with Java streams and its collector framework to get a very similar effect to the flatMapCompletable operator. And if you take a look at this link at the bottom of the slide, you'll get a chance to see how that stuff works. We don't really cover completable futures in this course, but it's still worth being aware of. Now that we've talked a bit about flatMap, let's go and have a deeper dive into the RxJava flatMap concurrency idiom. FlatMap is often used when each item that's emitted by a stream needs to apply its own threading operators. And once again, this is an example we'll take a look at in more detail at the end of this lesson. The way that this particular style of programming with RxJava and flatMap is known is referred to as the flatMap concurrency idiom. You can read more about it at the link at the bottom of the slide. So here's an example that we'll look at in more detail, but just a quick preview. We use the from iterable factor method operator to take a list of big fractions and convert it into an observable stream. And then we use flatMap to iterate through the observable stream, multiplying all the big fractions that are in that stream using a parallel thread pool. And you can see how this works. We take each big fraction that's emitted and we'll process it concurrently in the thread pool. And what we do first is we use the single class in order to essentially emit a big fraction. Each big fraction is emitted in a separate single. And then we use the subscribe on operator of the single to arrange to process the emitted big fraction in the parallel thread pool. That's the one we get with scheduler's computation. We then will multiply each big fraction using a thread that comes out of the parallel thread pool. And then finally, we use the toObservable conversion operator to convert the single back to an observable so it will work correctly with what flatMap expects. After all the concurrent processing is done, the final thread that's done in the pool that goes and processes and multiplies the last of these big fractions will then follow through and have the reduce operator called on it in order to add all the big fractions together. We talked about reduce, and we're going to talk about it again. It's used as part of a combining capability that RxJava provides. So now that we've talked about map and flatMap, it's time to compare and contrast these two methods. The map operator transforms each value in an observable stream into a single value. And it's really intended largely for synchronous, non-blocking, one-to-one transformations. That's one of the key things to remember. Map is always one-to-one. For each input item, there's an output item, which could be transformed in its value or its type, or both. In contrast, the flatMap operator transforms each value in an observable stream into an arbitrary number, in other words, 0 or more values. And flatMap is intended more for asynchronous, typically non-blocking, one-to-n transformations, or in some cases, n-to-one transformations, or n-to-m transformations. It's much more flexible in terms of how it's going to be applied. So that's the end of our discussion of the second part of key transforming operators that appear in RxJava's observable class.